All right, let's dive right in. We're surrounded by these incredible technologies with surfaces that are way stronger, more reflective, or better at conducting electricity than you'd expect. But how do they get that way? Well, the answer is usually a process we never even see, a kind of atomic-level sandblasting called sputtering. I mean, have you ever really stopped to think about it? How in the world do you apply a perfectly uniform, impossibly thin layer of something like a metal or a ceramic onto glass or plastic? You can't just paint it on, right? The secret is this fascinating process that builds these incredible surfaces literally one atom at a time. And this technology, sputtering, it's absolutely everywhere once you start looking for it. It's the reason the next generation of solar panels can actually bend. It's why industrial cutting tools can just slice through metal for hours and not get dull. It's even why advanced medical implants are accepted by our bodies. It's truly one of the great unsung heroes of modern manufacturing. So, let's pull back the curtain on these invisible, yet completely essential coatings. We're going to get into what sputtering actually is, and more importantly, how it achieves such mind-boggling precision. Okay, so at its core, sputtering is a type of physical vapor deposition, or PVD for short. That's just a fancy way of saying you take a solid material, turn it into a vapor inside a vacuum, and then let it condense as a super thin film on something else. With sputtering, the key words to remember are bombarding and ejected. We're basically shooting high-energy particles at a chunk of material to physically knock its atoms right off. Now, to really wrap your head around how this works, the best way to visualize it is to imagine a game of billiards, but one that's happening at the atomic scale. So let's break down this game of atomic billiards. Because, honestly, if you can get this analogy, you've pretty much got the whole idea of sputtering down cold. It's the key to how we get these precise, high-performance coatings. First, you need a perfectly clean table, so you create a vacuum by sucking all the air out of a chamber. Then you introduce an inert gas, something like argon, and you zap it with energy to create a plasma full of charged ions. These ions, they're your cue balls. You use an electric field to accelerate them and just, bam, you slam them into your target material, which is like the rack of balls. When a cue ball hits, it knocks atoms loose from the target. These atoms fly across the chamber and land on your substrate, say a pair of sunglasses, forming a perfectly even, ultra-thin film. And this little game is exactly why sputtering is so popular. Because those atoms arrive with some energy, they don't just land, they stick like you wouldn't believe. It creates a bond that's way stronger than just paint or plating. The process can also coat even the most complex shapes totally uniformly, and it works with a massive variety of materials, from simple metals to really complex oxides. But of course, that basic process is just the starting point. Over the years, engineers have come up with some brilliant upgrades to make sputtering faster, more efficient, and way more versatile to solve some really specific problems. So, the first big challenge is always speed. In any kind of industrial setting, time is money. So how do you speed up the rate at which you're knocking all those atoms loose? The answer, maybe a bit surprisingly, is magnets. This technique is called magnetron sputtering. By putting powerful magnets behind the target, you create this magnetic field that acts like a trap for electrons, forcing them to swirl around right in front of the target. These trapped electrons are way more likely to collide with the argon gas, creating this really dense cloud of ions. In other words, more cue balls right where you need them. More ions mean more collisions, which means a much, much faster sputtering rate. It's a huge boost in efficiency. Okay, so we've solved for speed. But here's a new puzzle for you. Standard sputtering uses a direct current, or DC, power source. That works great for targets that conduct electricity, like metals. But what happens when you want to deposit a coating of something that doesn't conduct electricity, like a ceramic oxide for a camera lens? Well, to solve this, we need a totally different tool. See, with DC power, positive ions hit that insulating target and they just get stuck. Soon, the whole target builds up a positive charge and starts repelling any more ions from coming in. The process just grinds to a halt. The clever solution is to switch to a radio frequency, or RF, power source. This thing flips its polarity millions of times per second, which neutralizes that charge buildup and lets the process keep on going. So the key takeaway is this. DC is your go-to for conductive metals, like putting a hard coating on cutting tool. RF is what you need for insulating materials, like an advanced optical coating. So we've got speed and we've got the ability to work with all sorts of different materials. Let's add one more super specialized tool to our kit. This one is all about getting the ultimate control over that final film. For some of the most advanced applications out there, it's not enough to just deposit a layer of atoms. The atoms themselves have to be arranged in a perfect crystalline structure. Think of it like building a brick wall. If you just dump the bricks in a pile, the wall is going to be weak and useless, but if you lay them in neat, ordered rows, it's incredibly strong. The exact same principle applies to atoms in high-performance electronics. So, the solution to this challenge is this really sophisticated technique called ion beam assisted deposition, or IBAD. This is where we go from simply depositing atoms to actively choreographing where they land. It's a major leap forward. So here's how it works. While the main sputtering is going on, IBAD introduces a second, completely separate ion beam that's aimed directly at the surface where the new film is growing. This beam acts like a tiny atomic shepherd, giving the landing atoms just an extra little nudge of energy. This lets them shuffle around and settle into the most stable, perfectly aligned positions, creating that strong, ordered wall we talked about. This process creates what scientists call biaxially textured films. And what's amazing is it does this without having to bake the substrate at crazy high temperatures. Okay, so we've seen the theory. We've got atomic billiards, we've got magnets for speed, and we have ion beams for perfect alignment. Now let's connect all these advanced techniques directly to the incredible products they help create in the real world. A perfect example is IBAD. That ability to create perfectly ordered atomic layers is the absolute key to building the foundation for next-generation flexible solar cells. As the research shows, this specific texture is what controls how efficient the device is. IBAD is literally paving an atomically perfect road for more powerful and versatile solar energy. And remember our workhorse, DC magnetron sputtering? Its ability to rapidly deposit dense, hard coatings of conductive stuff like tungsten carbide is absolutely critical in the manufacturing world. It's the reason a tiny insert on a cutting tool can withstand immense heat and friction, performing better and lasting so much longer. But the true power really comes when you start combining these tools. Researchers are now using both RF and DC sputtering at the same time to create these incredibly complex, multi-layered films. This lets them precisely tune the properties of a material, layer by atomic layer, creating things like transparent electronics, and they can do it all without high temperatures that could damage sensitive parts. So from the screen you're watching this on right now to the tools that built your car, sputtering is this invisible art of atomic construction. These impossibly thin layers, built one single atom at a time, are the foundation for so much of our modern world. And it really makes you wonder, if this is what they're building for us today, what will they build for our future?